on why we cannot really cover the actual dynamical parameter you expect for a astrophysical system, and especially how you should tune your resolution when you vary your parameters with magic, and how it should evolve, how much does it cost you numerically, and so forth and so on. So it's a lot of tricky questions, and I'm not even sure that I will completely address them correctly. But it's the first attempt to go towards this direction. So well, I will briefly give you an introduction, showing you what are the typical parameter regime of different astrophysical objects, both in rapidly rotating regime and in the weakly rotating regime. I will again show you some typical flow properties of this in different regime, although Uli briefly introduced this stuff already. And then I will try to justify what you should do when you're running some numerical simulation, what you should avoid to do, and is there some tricks that you can use to save some computational time, for instance, or things like that. So so it sounds like a very abrupt slide actually to start with, but now that you're getting a bit familiar with this dimensionless number, it should be fine. So it's just a summary of what are the control parameters of rapidly or rotating system, convectively driven system. So it's controlled by the Ekman number, which characterizes the ratio of viscosity over Coriolis force. It's characterized by the Rayleigh number, which quantifies the vigor of your convective system. And this is a ratio, or you can see it as a ratio of the buoyancy force over the different diffusive processes you have in your system, so both thermal diffusion and the viscous diffusion. Both Prandtl numbers, so the Prandtl number and the magnetic Prandtl number, can be seen as ratio of typical timescale in your system. So the Prandtl number is just a ratio of the thermal diffusion time over the viscous diffusion time, and then it's the magnetic diffusion time over the viscous time. So we can pick up some stellar object or astrophysical object and see in what kind of range of parameters they live. So on the first panel here, you see mantle convection, or a numerical model of mantle convection. So it's a very peculiar regime where you have extremely high Prandtl number, 10 to 10 to 10 to 10 to 3, and the Ekman number is also very high, which means that this flow is weakly influenced by rotation, and it has a, let's say, modest Rayleigh number of 10 to 8. So it's a very peculiar regime with also a very peculiar rheology, which then will, with a very complex viscosity that depends on the temperature value in a nonlinear way. Okay, on the other side, you have the sun. So now it's a completely different regime in a way, because Ekman number is very tiny. Prandtl number is also small, but Rayleigh number is extremely high, which means that ultimately the combination, as I will show later on, if you combine these parameters in a proper way, you can see that the sun is not really extremely influenced by rotation. It's more like as a side between the two regimes, because of the strong buoyancy forcing there. So in a way, you can, in a crude way, I can say, okay, these two are weakly influenced by rotation in a way. And at the other hand, you have planets, rapidly rotating planets. So the Earth here, with an, that's a minus missing here. So Ekman number 10 to minus 15 here, Rayleigh number of 10 to 27, strongly influenced by rotation. Jupiter here, with this nice banded structure, extremely tiny Ekman number again. Thanks. Okay, so in both the system, rotation plays really a major role in organizing the flow, as already Uli and Johannes showed you before. So if you can put like these numbers in sort of a summary table, you end up with this kind of table. So you have your control parameters here. What you see in the first glance, if you just take Earth's core and then the sun, Ekman is always extremely tiny. Rayleigh is always very big, right? That's what you can see right away. And then PM is also usually very small. But that's not all. I mean, you can also look at some other diagnostic quantities, like the SSR number, which quantifies the Lorentz over Coriolis force ratio, which is other unity for Earth and giant planets, which is a bit tricky to evaluate for the sun, simply because you have a lot of range of length scale and amplitude in the sun. So it's very hard to, give value, and probably Jörn would be more appropriate to give you some estimate of what should be the value I should put behind the question mark here. But probably the most interesting thing here for us is this Rossby number, which is basically telling you in which regime you might be. So if it's very small, it's strongly influenced by rotation. If it's larger than 1, it's weakly influenced by rotation. If it's other 1, obviously you are in a sort of mitigated regime in between. And that's where you can clearly separate the two categories here. So for Earth core, for giant planets, this is tiny, or at least it's significantly smaller than 1. For the Sun, it's around unity. So you can see it this way. So this local Raspberry number here can be seen as a ratio of the typical turnover time of your convective eddies to the rotation period. So, or the other way around, actually, the rotation period over the turnover time of convection. And so for the Sun, it's typically 1, because turnover time is like maybe a month, and then the rotation period is also a month. While for the Earth, I mean, the turnover time of convection may be 50 years, and well, the rotation period is a day, so obviously you're going to have some difference in there as well. So an additional complexity for the solar or for the stellar dynamos is that they exhibit very, very high Reynolds and magnetic Reynolds number, at least 10 to 9. You can play with this number again. It depends on which depth you pick up, so you can end up with even larger values depending on which reference value you pick up. While for the Earth, as Johannes said, as Uli said, it's a more intractable range, typically 1,000, which is numerically accessible, as I will show later on. Giant planets are in between. Again, it's fairly big numbers here. But in a way, I mean, it's, well, gives just a range of parameters. So what does it actually imply regarding the numeric? What can you do? Is it really possible to reach these kind of parameters? Well, I mean, it sounds like, okay, 10 to minus 15, why not, after all? So one way to already look at it is looking at Reynolds number, so the classical one, because they are always very big, right? 10 to 9, 10 to 12. So let's look at them. And the fundamental meaning of the Reynolds number is actually a ratio of two length scale. It's the ratio of the typical length scale of your system. Let's say, for instance, the thickness of the Earth core, or I don't know, the thickness of the convective envelope of the Sun, divided by the typical length scale, that is called the Kolmogorov scale. This is the typical dissipation length scale of your system. So when you have very big Reynolds number, it basically means that your dissipation length scale, if you have a Reynolds number of 10 to 9, let's say, your dissipation number is typically 10 to minus 9, smaller than the typical size of your system. Which would mean that ideally, if you want to resolve correctly such a flow, you would need to at least be capable of resolving this length scale as well as the bigger scale, which would tell you that you need crudely 10 to 9 points in any direction of your system. So you can put it in another way, saying that some people define a sort of mesh Reynolds number, so which is defined on the typical spacing you have between two grid points, and it leads you to a Reynolds number of unity, which should be the right condition to correctly resolve your flow. So right away, you see that you would need 10 to 9 grid points in each direction if you would need, or if you would follow this fairly crude estimate that I did here. So, and the run you did so far is typically 32 grid points in each direction. So here you see that, well, this might be an issue here. Okay. There is also an issue regarding time scale, obviously, and here the Ekman number might be a good candidate because, again, you can see it as a ratio of 2 time scale, as I said before. So it's just like a rotation period divided by the time to diffuse things viscously. And well, typically Ekman is very tiny, which means that now the viscous time can take approximately 10 to 15 times the rotation period. So if you want to do a simulation that both is capable of resolving the rotation period and be run long enough to also reach a diffusion time, you will need at least 10 to 15 times that. So which is again fairly impossible. So these two slides were just to show you some feeling on how challenging it might be to actually solve a proper astrophysical body in a numerical model. Okay. So what are the questions of this talk then? I mean, because now that you reach this stage, you can say, okay, well, you cannot do it. So, but one question remains entirely open. What can you do? So what can you do? What's the actual accessible parameter range? how much does it cost you? And how much, I mean, how should you regrade your parameter or regrade your simulation, refine it when you change your parameter, when you go towards less and less viscous flow, and so forth and so on. And how much does it cost in terms of CPU time, and so how much do you need to wait until you get your results and things like that. And the other end member is, can you do some compromise on the resolution? How do you know when it's under resolved or if it's over resolved? How do you have the feeling of these different questions? It's obviously very tricky to address all these things here. So, well, to try to go in the right way, I will just go back to some fundamental properties of rotating fluid dynamics, which we addressed, but I think it's good to just do it again here. So to do that, we start from the Navier-Stokes equation in the Boussinesq limit, which is given here. Here I made it dimensionless using the rotation period as the typical time. And this equation is basically controlled by two dimensionless numbers, the Ekman number here, and the parameter that we call for now R star, which is just a modified related number. I will come back to that just briefly. So we saw that Ekman is very tiny in all aspects of the physical system. So viscosity is a tiny player, and well, it requires some additional assumption here, but let's say we can drop inertia in the first place as well. So we end up with the three terms: force balance, Coriolis force, pressure gradient, and buoyancy. So now what means RA star, and how big is this guy? So RA star is actually this combination of the parameter Rayleigh Ekman square over PR. So some people like to call it the corrective cosmic number, and this is supposed to be a proxy or a relatively decent proxy of the ratio of two forces, buoyancy over Coriolis force. So right away from this equation, you see that you will have two regimes. The first one, when R star is very small in front of unity, then basically can kick out this term, and you end up with Coriolis. That's what we presented here. And this is going to be the columnar regime and proportion and so on. The second regime, where R star becomes over unity or larger, and then you can left and you enter into a second dynamic regime, which is fairly different from the strongly or rapidly rotating action. So, well, let's try to identify a little bit the properties in these regimes. So the first one is R star very small in front of unity, strong infinite by rotation. So as I said, you can just, cross this term here, and you end up with two terms force balance, Coriolis pressure gradient. You take the curl of this equation, which has the property to remove the pressure gradient, and which leaves you with this very simple equation: du is equals 0. This is the so-called Taylor-Pronman theorem, and what it tells you is that the flow is going to be independent of any variation along the axis of rotation. So which means that as a consequence, convection will take the very peculiar form of this columnar structure aligned with the rotation axis. And here are two examples provided by Johannes. The first one has a still fairly large Ekman number 10 to the -3 and a star rated number of 0.1, which makes it small, but not extremely small, I would say. It's very benchmark-like solution, so very similar to what the rendering of that you did yesterday in a way. But still, already you see this nice alignment of the column with the rotation axis with some feature are also dependent. That also shows some variation along the rotation axis. If you do a first jump in this direction here, you decrease your Ekman number by a factor of 30, and you end up with the R star, which is now 10 to the -2. It's strongly dominated by rotation, and you said your flow is strongly constrained now. It's a rigid flow in a way, nicely aligned with rotation axis, strongly constrained by rotation, with very little z variation, except due to the sloping of the boundaries, obviously, that you have to fulfill in a spherical container. Well, just as a parenthesis here, I did the reasoning without magnetic field. I can always complain about it, saying, okay, if you have an S on unity, it's going to stay here, and this stuff will hold, and so forth, and so on. So I just make clear that, with the magnetic field on top of it, it might be even more complicated than that. Okay. So what are the properties of this typical rapidly rotating system? So I have no time to demonstrate it here, but what you can feel already right away when you decrease your Ekman number is that your flow is more and more constrained by rotation. It means that the onset of convection at all will be delayed when you increase the rotation rate, if you want. So it translates into this formula that the onset of convection is inversely proportional to the Ekman number. So if you make it your flow more and more influenced by rotation, it's more and more constrained, and you have to drive the way your system stronger to get convection at all. So you have this flow here that you can demonstrate at least in some peculiar geometries. So I have no time to show you the details here, but you can show first that it's critical. This onset depends on Ekman 4/3. And the second thing you can show is that the typical length scale of your picture here depends on Ekman 1/3. So which means that if you decrease it, if you go to more and more rotation influence flow, you're going to increase the number of these columns more and more, and have smaller and smaller and smaller pictures. And that's a tentative visualization of that on a broader range of parameters. So these are purely convecting system, no magnetic field at all. They are approximately 10 times supercritical, so which means that your Rayleigh number is typically 10 times larger than this value here. And they operate, the three cases are at the same supercriticality. The first one has an Ekman number of 10 to minus 4, then 5, and 6. And what you can see right away is that the typical size of your feature here are getting smaller and smaller. So, yeah.
Just have a quick question. But does the velocity increase in that scenarios or decreases? So the kinetic energy?
The kinetic energy increases because, it's a tricky question in a way, but your Reynolds number increases as a dependent on Ekman number, so it's going to increase at the same. If you keep the supercriticality constant, decrease the Ekman number, Reynolds number will increase. With the power of Ekman, well, it's debated, but let's say 1/2 or so. But it's, yeah. So the thing is that here it seems to provide a path. You have this length scale 1/3, and right away you can say, okay, if I want to put an appropriate spatial resolution in my simulation to be capable of correctly resolving this different simulation, I will need to regrid accordingly when I do these jumps. And this little Ekman 1/3 rule provides sort of path to regrid correctly my system. Okay, so this was the first introduction for the first regime. So what happened when R star gets larger and larger? Then, as I said, it becomes a personal contribution here, and you start to have a more complicated flow. So these are the two cases. So this is a simulation. Well, this is exactly the simulation I showed before. This one here, 3 × 10⁻⁵, R star of 10 to -2. And now what I did here is just, Johannes actually did it. You multiply the Rayleigh number just by 5 roughly, and what you see is just you start to observe a very strong breakup of your columns. Now you have some flow which really will depend on some variation. It's getting much more fractured, much more small scale. So what you can see is right away, okay, this Ekman 1/3 rule is going to be a bit tricky because when you change your convective forcing, obviously the length scale changes as well, so you may need to refine your grid on top of that. So that's precisely the purpose of this sentence here. An increase of R star is an increase of the Reynolds number, and therefore you may need to refine your resolution as well in this direction. So, and the thing is that now, how do I regrid my stuff? And this gets very complicated here because you have to answer this question: how do the length scale evolve to the Reynolds number? And this is a good question. So what I'm here is that I just stick to a regime where I start stimuli in front of 1. In that regime, then you're typically reaching a regime where rotation doesn't matter. So it's essentially a non-rotating system, if you want. And in that case, you can use as an upper bound that your typical grid spacing, or the spacing between 2 following points in your numerical domain, has to be smaller than the Kolmogorov, which is the typical dissipation scale of system. And you can furthermore show that this Kolmogorov scale is equal to the ratio of the viscosity to the power of 3 water by the viscosity to 4. Right. Good thing is that So we did one step more. So the good thing is that the viscous dissipation rate relates to this property exactly, or is proportional to this quantity in convectively driven flow. So it relates to the Rayleigh number, to something. Uh-oh. Well, it's still here. Shit.
Yeah.
Mm-hmm.
Can you say again?
I can unplug replug.
Yes. Should we have in mind? No problem. We switch it out on. But this will take some time because it has to cool down. Switch it out. And then you have to wait because it needs to cool down. So small break.
For that, guys.
Just in case, but try again to switch it on. It may have overheated, but you wait too busy. So it needs a moment to cool down, a minute or so, and then you can try again.
Well, I can take any questions if you already come from my beginning of my talk. So. Okay.
So,
It's a digestion time.
bottom up basically also show you the depend on each other. Right? So the radiant number depends on Ekman, for example. And if you start changing one of the parameters, it doesn't necessarily make sense to keep parameters constant. So if you decrease the Ekman number, it's a good idea to increase the Rayleigh number, according to, for example, the rule that Thomas showed. Otherwise, you compare two different simulations that may run in completely different regimes. So it's worth to think about it. Sometimes people forget that and they publish in Nature papers. But according. Similar, it's with the magnetic frontal number, for example. We will see this maybe later when Ankit has collected our results. So generally, it's a good, so you cannot decrease the magnetic frontal number indefinitely. Because think of the magnetic frontal number as electrical conductivity, for example. So when you decrease your electrical conductivity in the system, then your dynamo has a harder time to survive. And to compensate that, you have to increase velocity. So remember, we have this important parameter which is called magnetic Reynolds number. This is basically velocity times electrical conductivity. And that has to be larger than a certain value. So when you decrease the electrical conductivity, you have to increase the flow speed to compensate for that. So if you decrease PM, you have to increase Rayleigh. That's the equivalent. That shows you another dependencies of the parameters. So can switch on again. I hope that helps.
There's no warning sign.
No. There's something blinking, right? Red.
Oh, it seems to.
That's the power. Okay.
I need your power. check on yours and check
If that fails, we have to use the spherical method. But there was something. There's something there. Okay. Oh, let's hope it doesn't happen again.
Okay. So we're back here. So I was just talking about this dissipation rate. So you can show that it should be proportional to this quantity here. Luckily, there are two parameters that you directly control here: the Rayleigh number and the Prandtl number. There are two key parameters that you have a handle on. Well, the sad thing is that this mu here, it stands for the Nusselt number, and Uli, I think, introduced it briefly. It's the ratio of the total heat flux you can carry divided by the heat that would be conducting if you would have just a purely conducting system. So let's put it in another word. If mu equal 1, it means that the whole heat is carried by conduction. If it's larger than 1, it means that some convection is typically taking some fraction of the heat transfer. So let's take, like, if you take mu equal 2, it means that at least 50% of the heat is carried by means that more and more heat is carried by convection, which is what you would expect for any astrophysical system where convection is efficient and strongly carries most of the fraction of the energy. So here basically, even if you cast this expression into this system here, you have no way to get what your delta is. So what you can do here is put an additional assumption that holds fairly well in non-rotating convection. That is that Nusselt number scales as a function of Rayleigh to the 1/3, which is, more or less fulfilled. And in that case, you end up with this formula here, which gives you a rule of how you would possibly rescale the grid size or the grid spacing as a function of the Rayleigh number. But again, this is only in the limit of very extremely high Rayleigh number. And this is another asymptotic regime. So I showed you like very small in front of 1, L equal 1/3. Very big in front of 1, and you have this rule, but in between, things are getting a bit complicated. So I'll come back to that a bit later on. So, okay, so now let's see what happens if you try to more or less follow this path. And let's focus on rotating convection now a little bit more. So what does it effectively mean if you follow this Ekman 1/3 rule? So the case you've been running are typically here. Ekman 10⁻³ and typically in the range of 64 cube simulation. Typically, I mean, you use maybe 33 radial grid points, and you use 192 grid points in phi, which translates into a maximum spherical harmonic degree of 64, and a maximum spherical harmonic degree of 64 as well. So it's typically in the range 64 cube. What the Ekman 1/3 rule tells you is that each time you divide by 10 your Ekman number, the resolution goes with 10 to the 1/3, which is approximately 2. So each time you divide it by 10, you have to multiply your resolution in each direction by 2. So it means that something which was 64 cube here at 10⁻³ becomes 128 cube at 10⁻⁴, 256 cube at 10⁻⁵, and so forth. So it means that on each step, you will need to refine your system more and more, and it's going to be more and more expensive to resolve numerically, obviously. So the second issue is the time step. So what happens when you decrease the Ekman number? Well, basically, as Johannes showed you this morning, Coriolis force is treated explicitly, so which means that the code cannot run faster than the rotation period. So even if you take the rotation period as the maximum time step you would be allowed to run with, each time you divide your Ekman number by 10, it means that as a consequence, the maximum time step you will have will be divided by 10. So in other words, let's pick up a solution. Ekman number 10⁻⁵, PM of unity. And let's assume we want to run one magnetic diffusion time. And let's do a very crude assumption, which is we can run with a maximum time step of 10⁻⁵. Then we simply need 10⁵ time step to cover 1 magnetic diffusion time. But what happens when you go to 10 to minus 7, for instance, here? The thing is that, okay, you will make, as Johannes mentioned, you may be able to decrease a bit PM. So let's be optimistic and assume you will be capable of dividing it by 10. Then to run 1 magnetic diffusion time, you will need 10 to 6 time step with a grid which will be multiplied by 4 in each direction, right? So that's going to be very complicated. And there are further additional caveats here. Here I made a very crude assumption that practically you will be able to run at 10 to minus 5, which is exactly the rotation period. So doing 1 time step per rotation period, which is never going to happen. Actually, you're going to have a CFL, Courant-free heavy condition, which will tell you that you may run maybe at 0.1 of the rotation period or something like that. So it's likely that the actual numbers you may need is 10 to 6 here and 10 to 7 here, and so forth and so on. Additionally to that, you might have some additional propagating phenomena such as inertial waves and so forth that might kick in when you decrease the Ekman number, and that might further reduce your allowed maximum time step. Okay. So this is a sort of fancy diagram that I picked up from a review paper by Paul Roberts and Eric King. And this showed you sort of a minimum Ekman number versus time. So you start with the first dynamo model by Gary Glatzmeyer and Paul Roberts, published in '95, which is hardly influenced by rotation in passing, right? It's an Ekman number of maybe, well, you see it here, 3 × 10⁻² or so. And then, of course, well, computational power improves over time, so you can, push this limit a little bit more, and you end up with this sort of winding path where you have some dots, well, scattered a bit around, and you end up with your 2012 values. Let's say around 10⁻⁶ is the minimum Ekman number published today. So that was published in 2013. So I added a couple of dots here. Oh, and by the way, you have this fancy scaling here that we tried to derive, which is supposed to predict the Ekman number you may get as a function of the year minus 95. So it's normal. It's a Glatzmeyer normalized scaling number. So what happens here is that I try to have some, well, simulation that have been done so far, which are either not yet published or published in PhD thesis, such as the simulation by Sheko in 2014, which slightly pushed the limit a little bit. So, well, the more recent jump is by Nathanael Scheffer. So he recently, well, did a simulation with an Ekman number of 10⁻⁷, which is here. And I put some question mark with an additional dot for next year because, well, there will be this Rayleigh code, which was developed by Nick Featherstone, which is ambitious and which is claiming that they are capable of reaching 2048 cube resolution in spherical shell. So according to my little diagram here, it would be here. You would be able to do this last jump and go to 10⁻⁸. So that's why I put this last dot, which is saving the scaling, right? This is the only dot which is like above the line, so you can save it, and indeed it still holds more or less. So let's do it, extrapolate it. 10⁻⁵, 2038. That's it. So the geodynamo problem might be solved in 23 years, It's no big deal. Okay, so just to show you how it looks like then, if you really go to the state-of-the-art simulation, you put the maximum, grid size. So it's like typically 1024 cube class simulation, Ekman number 10⁻⁷, Rayleigh 10 to 13, and PM.1. You see this very tiny scale structure, especially close to the outer boundary. But on top of that, you have also fairly, well, bigger scale that you can see, especially close to the inner boundary here, which might be the sign of an inverse cascade that I will discuss a little bit later on. So, but to just give you an idea, so this is a simulation by Nathanael Scheffer, 1034 cube class simulation. It takes roughly 1 to 5 million CPU hours to get it done. So that's fairly big. So if say you would have 1,000 CPUs, it would mean that you would run 3 months full time to get it. Right. So how much would cost the next step? So 10⁻⁸, which is like the target value by the Rayleigh code. You go to 2048 cube class simulation, then you end up with 10 to 50 million CPU hours. Again, assuming that you can now run on 10 to 4 CPUs for 3 months, which is something that you don't necessarily have, you know. And I'm not even talking about outputs here, so which going to be, well, you're going to have massive output files, so you have to find your way to dig through the data and store the data, analyze the data, and so forth and so on, which are additional complexities that I will not touch here. But obviously, if you took like the G files you did yesterday, so you all play with Paraview and so forth and so on, you had some files which were like, I don't know, 10, 15 megabytes. Here it's going to be like terabytes. So obviously, you will have a hard time to just load the data and do something with it. So you have to rethink your whole analysis or do it, you know, on the fly during the run to get something meaningful that you could extract from this kind of big simulation. Right. So, and obviously an underlying point is that, well, to do this jump here, you have to make sure that your code should scale on 10,000 processors, which means that the underlying assumption is that you're capable, you have a high parallel efficiency in your code. That's obviously mandatory if you want to continue along this path here. Okay, so let's go back a little bit to this Ekman 1/3 rule. So is it so strict, and what could you expect when you reach low Ekman number regime? Especially one issue with this simple Ekman 1/3 rule. What happens if you extend it to Earth? So well, we end up with L over D equal Ekman 1/3. So D being the thickness of the inner core, the liquid core, and then Ekman 1/3. So you take 10 to minus 15. So 1/3 gives you 10 to minus 5. Let's say you take roughly 1,000 kilometers for the thickness, gives you 10 meters here. So which would mean that your columns would be like 1,000 kilometers long and 10 meters thick. So it sounds like a little bit crazy, right? This would be like an extreme spaghetti thing, which would be extremely thin, 10 meters and 1,000 kilometers long. So that's really questionable if it's going to be like that. And luckily, you have some phenomena that could cascade some energy towards larger scale. And one of the reasons of that possible, you know, cascading of energy towards larger scale is the rapid rotation, the inherent rapid rotation of the system, which means that the flow is strongly bidimensional. So it's essentially a two-dimensional flow, as you can see here in this nice simulation by Stefan Sternmann. And well, the theory tells you that if you have a 2D turbulent system, it essentially is capable of producing some inverse cascade and produce larger and larger scale. And the nice thing is that you do see that in the box simulation that have been carried on by Stefan Sternmann here at low Ekman number. So you see the formation here, for instance, in this range of very large vertical structure, which are getting much bigger than the typical size of the convection feature that you should see with the simple Ekman 1/3 rule. And you sort of a little bit see that, although it's less convincing in this simulation here, where you also have a lot of energy in this fairly large scale structure. I mean, fairly large scale. They are still tiny scale, but as compared to what you have close to the surface here, which would be maybe closer to the Ekman 1/3 rule, you have a lot of energy in sort of intermediate scale in there. So that's what I state here. Typical length scale might be much larger than Ekman 1/3. That's sort of a good news that might help us a little bit. So, well, this is a sketch that I took from John Onumu that in a review paper that he really recently wrote. So you have a sort of laminar somehow view where you assume that the typical length scale of your columns would follow this Ekman 1/3 rule. So of course the sketch is not really good here because it would be extremely thin spaghetti, 10 meter wide and 1,000 kilometers long. On the other side, if the inverse cascade happens as observed in the simulation here, well, you can show that the typical length scale of the structure you should have should follow the so-called Rhine scale. So I won't enter into the detail here, but you can show that it has this scale with the square root of the Raspberry number. And applied to the Earth, you would end up with roughly 60 kilometers. So then instead of this sketch here, you would end up with this right panel where you have very little, well, this L-conv here would be the very little structure, which follows this Ekman 1/3 scaling typically. But on top of that, you would have fairly big scales, typically maybe a couple of, well, 10 kilometers or 100 kilometers thick, which could then be more likely to span the entire core in the vertical direction. But here, I mean, here I'm a bit entering into the speculative question that are debated and strongly debated by the community, but this is just to give you a feeling on how things could behave possibly. Okay, another hope and is that when you decrease the Ekman number, you're, well, I has answered the question before, when you decrease the Ekman number, your flow is getting more and more turbulent at a fixed supercriticality. And by doing so, it means that it's likely that the equilibration time of your system is getting a bit smaller than what you would have for a purely viscous flow. So, and instead of, I mean, which means, practically it means that you may not need to run one full magnetic or viscous diffusion time to get your final thing settled, but a fraction of that might be sufficient to get something which is already saturated just because you have a harder degree of turbulence. So, well, rule of thumb, really, is that here you can more or less say that the time you would need is a sort of multiple number of the typical turnover time you have in your system. And this turnover time is typically 1 over the Reynolds number. So let's say that after 10-ish or so turnover time, your system would be equilibrated. Then you would say that the running time you need is inversely proportional to 10 over the Reynolds number. So which means that when you get towards lower and lower and lower Ekman number, it might help a little bit regarding the runtime you need. And that's what actually happened in, well, I don't have the time series here, but that's precisely what happened in the simulation by Nathaniel Schaeffer, where the whole solution equilibrates, let's say, in a much faster way that you would have for an Ekman number of 10 to minus 4 or something. Okay, there are some issues, though, that you have to keep in mind here. The stability of the dipole, if you play this game here that is running your simulation shorter, you might not be able to say much about the stability of the larger structure of your system, which is the dipolar magnetic field, because this one might take really long time to diffuse. So it's going to be the longest diffusion time you have in your system. So if you run only a fraction like that, most of the small scale are going to be equilibrated for sure, but you don't know about the dipolar stability. So that's something you have to keep in mind here. Okay. Of course, this is all. Well, you can cast a lot of additional problems in there. I briefly mentioned them already. This Ekman 1/3 will break up eventually when you increase the forcing. So you have additional complexities here. You have a dependence of the resolution on how supercritical you drive the system. And the odd limit would be that the spacing between 2 grid points is smaller than the Kolmogorov scale, which brings us back to this formula I already mentioned. The thing is that, again, we don't know in practice how Nusselt or the heat transport depend on your input parameters, Rayleigh and Ekman. And what you can do is, like, you can play around with that a little bit and, well, use 2 possible asymptotic laws. So the first one being strongly or rapidly rotating convection. Then Nusselt numbers might scale like that. And you might end up with a scaling like that. Actually, I messed up the 2 columns here. So it should be this one here. And if it rotates slowly, then it should be this one here. But yeah, I mean, there are a lot of debates. It's not clear that this stuff holds the whole way and so forth and so on. And this is a sort of odd limit here. So you might still be able to compromise a little bit here and have like a mesh which is like slightly larger than that, especially with spectral method, since the spacing is irregular. So we have more grid points in the boundary layers where most of the dissipation happens. So it's like a fairly crude and order of magnitude thing that I'm doing here. But in general, that's a very complicated topic here. So let's put it in a sort of summary table here. So this is the Earth value, 10 to minus 15, 10 to 27, Reynolds number of 10 to 9. So what I call like tractable is the thing you could possibly do if you have more or less 1 million CPU hours, and if your code scales relatively well, like the magic code, for instance, you could possibly reach 10 to minus 6 Ekman number, reach 10 to 12 Rayleigh number, and maybe, well, actually here I was a little bit pessimistic. I think you can reach maybe 5,000 or so for the Reynolds number. It's a lot of tractable regime. Now, if your parallelization is really good, if you have very efficient code, if you have 10 million of CPU hours or 100 million, then you can mine GANs one step here. The odd limit now in 2015, so just like one order of magnitude better here. And well, a bit better in terms of, turbulent regime. They nearly reached 10,000 for the Reynolds number, which is, toward the right path at least. Okay, now let's move to the next chapter, which is the downs. So what you should avoid to do, and how do you know it's under resolved, and what are the signature of under resolution while you're running something with Magic. And here I'd like to thank Ankit for his nice under resolved English provided. So, well, the first thing, and Johannes, I think, already told you that, always look at the simulation. Always look at the solution, how they look like. Are they like meaningful or not? And well, a possible thing is you just do a radial cut in the boundary layers. That's what I did here. So I pick up just radial velocity at the radius of 0.99, the outer radius, so which is typically in the boundary layer of the flow. And what you see here is this kind of messy thing for the radial velocity. And for the magnetic field, you start to see these so-called eyes. So it's a sort of like if you would throw a stone into a lake or something, then you would see this kind of thing where you have these ripples here, and it's changing polarity very suddenly. So it's a clear sign that here your grid might not be sufficient. And another thing is that here for this one, well, I know that the structure I observe here, the small scale stuff, because after all, you can say, okay, maybe it's physical. After all, maybe my system produces that. But the thing is that I know in advance here that the spacing, the grid spacing I have, is of comparable amplitude as the feature I see here, which is already very bad because it means that you have a lot of energy in the smaller scale you can resolve. So it's an obvious sign of under resolution. So that's the first thing you should look at. Look at the solution always. That's the rule. The second thing is you can check spectra. So spectra, here they are average of the whole volume, at least for the kinetic energy. So they might be a little bit misleading because if it's massively under-resolved in one portion of your domain, it might be smoothed out when you look at the global spectra, which are integrated over the whole volume. But still, they provide you something. And here, especially, what you see is that your kinetic energy hardly decreases by 2 orders of magnitude, which is really, well, sort of maximum or minimum thing you should consider. So you should have at least 2 orders of magnitude between the injection scale and the small scale in your system. That's, well, a recommendation. The thing is that for the magnetic field, you don't even have that here. So what's plotted is in black, the toroidal magnetic spectra, in blue, the toroidal magnetic spectra, and in green, the spectra, the surface spectra, which is a 2D spectra. So it's very interesting because it's going to basically give you that here, more or less. And you see that it's very bad because you have only 1 magnitude here. So it's not very good. It means that, well, your solution is not converging very nicely, and you might have some issue here. Okay, you have some additional diagnostic that I have no time to discuss about. We can talk about them later. You can, for instance, check the influx conservation. That's very important. So you have to check whether the influx that comes in from the inner boundary comes out as the outer boundary. So everything that comes in has to come out. That's the first thing that has to be conserved. And this, usually if you have some resolution problem, it might be an issue. So you might have some difference between what comes out and what comes in, just because you have some dissipation occurring at some levels you don't control. The power budget is also very interesting. So you can just compare what's the buoyancy power input you have, which is what's provided by the conductive forcing, compared with what is dissipated viscously. So without the presence of magnetic field, they should exactly match, at least in a time average sense. And again, if you're slightly under resolved, you'll quickly notice that these 2 numbers will differ by a few percent, maybe 5%. So 5% doesn't sound very big, but already it means that you may have some very serious issue regarding the spectra and the local properties. So let's pick up another example, because after all, you may say, okay, maybe it's not so bad, actually. I mean, I already have 1 decade here, so why not? Why not trusting this solution? So let's pick up another case. So this one, the good thing is that I have the two cases, the one which is under resolved and the one which is going to be resolved correctly. So we can really compare them. So what you see is the radial velocity, again, very close to the surface, the radial magnetic field. So it's extremely small scale. And you have this lot of salt of paper thingy at very small scale, all these little dots here. So you can say, well, it's a granulation, you know, it's like a solar granulation feature. But actually it's not, it's just like very comparable to the grid size you have here. So which means that, again, you have a very lot of pileup of energy in these very tiny scales here in there. So it's like a, yeah, it's like a very, like CRT rendering from the 70s, and then if you go HD, so you just multiply the resolution by a factor 3 or so, then you smooth out everything, and now you have the clean solutions. You basically see that all these very tiny little scales that you had in there and in there, well, most of them are nicely resolved now in the flow. Well, the magnetic field is not perfect, as you see here. There are still some little issue, but it's already much better. Of course, well, you can say, okay, the conclusion was I just need to multiply the resolution by a factor 3, and that's it. But the thing is that it's computationally much more expensive to resolve this second case. So the question you may ask is, well, is it that bad? So these are the spectra. So the green line is the under-resolved. The blue one is the resolved case. This is the global volumetrically averaged quantities. And these are the surface quantities. So what you see right away is that the green line, well, on the volumetric quantities, you have more or less your two orders of magnitude decay. You can say, okay, that's fair. But of course, if you look at the surface spectra, then you're really in trouble. It's flat, nearly, and it even piles up at the end. So which means that you really have like a strong peak of energy at the really tail of your spectra. So here you really have a lot of trouble. So obviously, you smooth it out nicely when you increase the resolution. Although the surface still has some pile up, as you can see here at the end, but it's much better than it was with the green case. But the thing is that, surprisingly, and still I think there is no obvious answer why it should be like that, the larger scale are reasonably well captured. So even if you have completely under-resolved thing, the larger scale up to, let's say, a spherical harmonic degree of 30 or so, they are not completely stupid, they are close. So which tells you that maybe, even if it's under-resolved like the salt on paper simulation, you might still have some global RMS quantities, volumetrically averaged, that might be still okay. And to illustrate that, what I did here is just I compared two quantities that came out for these two simulations. So first, the volumetrically averaged quantities. The magnetic Reynolds number didn't change. The SSN number didn't change. But obviously, the surface quantity is going to have a lot of trouble. So this SSN number at the surface is nearly divided by 2. And the heat flux that comes out, obviously, so I was mentioning this heat transfer issue. So well, ideally, if your simulation is correctly resolved, the heat flux that comes out has to be equal to the heat flux that comes in. So you should have Nusselt air out equal Nusselt Ri. And obviously, in the resolved case, it was not the case here. You had a strong mismatch in the heat flux. So when you go to the correct grid, then they match again. But again, that's pretty surprising. But well, it's under-resolved by a factor 3 or so. But your average volumetric quantities might be good. So I would say it really depends what you're after. If you just want to look at RM and it's as a number, you're fine. But if you start to look at local quantities or surface average quantities, and especially for deriving scaling laws, you might need this Nusselt number here. Then you have to be really careful with what you're doing. Otherwise, you might just introduce some, error in your data set just because you have one run which is under-resolved. Okay. So to sum up this section, in general, I would say Beckman wants to provide you a sort of path for rotating convection that you should follow when regridding and when adapting your truncation and rerunning parameters. In details, it's not so simple because the convective forcing also matters and also has an impact on the resolution. So you have to be careful and check your solution each time you run something. So what is a sign of a good resolution? Obviously, no eyes, no specific features in the boundary layers, clean spectra, no problem in the power budget, no problem in the transfer. That's clean. Bad resolution, it means, well, this localized pileup of energy at the tail of the spectra, no proper dissipation range, and so forth and so on. Totally bad resolution. So what happened here? Hopefully, the solution should crash. So if you're completely off, so if you use, I don't know, 32 cube and run a 10 to minus 6, Ekman number 10 to minus 6 simulation, the run should blow up just because you're completely off. You're not even capturing the injection scale in your system. So then it should blow up, hopefully. Okay, the good thing is that you can compromise a little bit around, and especially if you're looking only at volume integrated quantities, it might be cheaper to, run some simulation or under-resolve a little bit your simulation if you're only after volumetric integrated quantities. So again, big caution here that what you're doing is slightly under-resolved, and therefore the local properties like the heat transfer and possibly the scaling law that you may derive here might be wrong just because you are locally wrong, and especially in the boundary layers. Okay, the other problem is that you don't want to overdo it, so you don't want to over-resolve your system because large resolution are very expensive numerically. So you have to find the right range of parameters or the right setup for adapted to your physical parameters. Okay, so is there some tricks that you can use to ease a little bit your simulation? I will show some of them here, and probably you might use some of them even in the run after in the hands-on session. So the problem with convection-driven dynamo is you have very long transient. And you don't want to waste all your available CPU times in these transient phases. So what you could do is, why not running a little bit under resolve during the transient, and then refine your grid once you're settled. Of course, you cannot massively under resolve the thing, otherwise it will blow up, but you can do a compromise a little bit as this salt and pepper solution that Rakesh did. So here is an example. So you have a first grid, which is 100 grid points in radius, spherical harmonic degree maximum 220, spherical harmonic order same. So I didn't mention it yet. And you run it with 100 CPUs, and it takes approximately half a second to run one time step. So to run 10 to 6 time step with this situation, it would take you approximately 15,000 hours of CPU time, which is reasonably okay. Now, what happens if you would start right away with this one? Then you would obviously use a much higher number of processors because you have no choice. And still, your world time wouldn't be that good with this configuration. So you would have 4.4 seconds here, which means that for 10 to 6 time step, you're going to need 1 million CPU hours. So for running the same number of time steps. So which means that if you start your simulation right away with this configuration, you will burn your CPU times just in the transit. You don't want to do that. You want to have a sort of compromise resolution, pass the transient, reach the plateau, and then refine the grid. And possibly check if it's stable or not, or something happens, right? So yeah, big resolution is expensive, and I'm not talking about the data storage, which is again an issue because, yeah, all outputs is going to be bigger, especially the 3D files. So yeah, make sure that you use them only when really required. The second thing is that you can more or less follow a sort of meaningful physical path when you change your parameters. Especially, let's say you run most of you run this, or all of you run this simulation at 10 to minus 3, and then obviously you may want to decrease the Ekman number. And then the thing is, how should you do it the nicest way in a way? So one possible option, which is supposed to work fairly well, is to keep the same supercriticality when you change your Ekman number. If you do that, what's going to happen is that your thermal equilibration time is going to be much smaller, because usually if you keep the same supercriticality, your Nusselt number remains the same, or in other words, the thickness of the thermal boundary layers don't change. And if you do that, usually the equilibration time is reduced a little bit. So which means that for instance, if you have this run already available, you want to go to 10 to minus 5, you do this jump by setting up, so your Ekman number, you have the new one, it's going to be 10 to minus 5, and your new relay number is going to be the old one times the ratio of the old Ekman on the new Ekman divided by 4/3. And you can follow the same thing on the second jump. And that's, for instance, the path that Nathaniel Shepard followed to reach this 10 to minus 7 weight and eliminating the maximum transient phase as he can, just by following this meaningful path here. So that's a possible path that you can follow when you are doing rotating convection. Okay, another trick that you can use, which is mainly applicable to non-magnetic simulation, I would say, is to solve for only a fraction of the spherical shell. So instead of solving for the full azimuthal range, you just solve for a chunk. So it's like solving for a quarter of the shell or half of the shell, something like that. So this can be controlled, as Johannes mentioned this morning, by an input parameter named mink that you can see in the name list, which is by default to 1, which means that you're solving for the full range of azimuths. But you can possibly set it to 2, to 4, to 8 to solve 1/2 of the sphere, 1/4 of the sphere, 1/8 of the sphere. So here, for instance, I use the symmetry. So can you see that? Yes. So if you take these pairs here, they are also here. So it's exactly the same columns feature coming here, and probably coming here. So you have a mink or a 4-fold symmetry, which means that effectively in this simulation, I was just simulating 1/4 of the azimuthal range. Now the question you might ask is, and I mean this was a very low Ekman, 10 to minus 6, strong driving. So it's a strongly turbulent case, as you can see. It has a very large range of scales, very tiny scales here in this region, large scale here. So it's a pretty demanding simulation. And the thing is, now the question is it really important to solve only for 1/4? I would say it's fair as long as the typical length scale of your flow is smaller, is much smaller than the chunk you're solving for. So if, say, I would have typical columns of this size, then obviously it wouldn't work that well. And again, you can do some comparison. That's what is done here. So these are two simulations, one with the 8-fold symmetry, one with a 2-fold symmetry. So 1/8 of the sphere, 1/2 of the sphere, exactly same properties. Nusselt number same, Reynolds number same. And the thing is that this one was run with 200 CPUs with a hold time of 1 second, which cost me, well, let's say 50,000 hours for 10 to 6 time step, while this one is already in the 1 million CPU hours range because of the increase of the hold time here and the number of processors both. So this sounds like a very nice trick. So you could say, well, why not doing that all the time? The thing is that if you do that, it works fine as long as you're doing convection simulation without magnetic field. But as long as you will put the magnetic field in there by just, putting some symmetries, you will, for instance, suppress the equatorial dipole. So you will not allow your simulation to be like an equatorial dipole, which might have a very strong drastic consequences if you're looking at reversals of the magnetic field, just because there is no way. I mean, it can flip from one side to another, but there is no intermediate stage because the equatorial dipole is filtered out. You have to be really careful when you use this symmetry approximation and doing dynamo models at the same time. But I would say if you want to do that still in dynamo models, you might use this trick during transient phases. So you just do your transient, then it's saturated, it's cheap, and then you demink. So you remove the symmetry somehow. So you move from your symmetry, which is maybe 4-fold at the beginning, and you remove it, and you see whether things change or not. That's a possible thing for the magnetic case. Okay, the last thing I want to mention here as a trick is the hyperdiffusion. It's not such a clean trick, so I put dirty trick here because, well, you can argue a lot about that. So what is hyperdiffusion? What is this silly thing? So it's a sort of additional diffusivity that you introduce in your system. So instead of having classical diffusion, you now have a viscous diffusion coefficient that explicitly depends on the scale of the flow. So instead of having a constant kinematic diffusion, you have a diffusion that depends on L. And it depends on L as this function here, which has basically a free parameter beta that you can tune, but usually you assume beta equals 3. So what does it mean? It means that you're going to damp more severely the small scale as compared to the large scale. So effectively, it means that the small scale are going to be damped much more. And well, it's basically as if you would add a sort of square Laplacian U or a cubic Laplacian U into your Navier-Stokes equation, and add it as an additional viscosity. Of course, if you do that, you will damp severely the small scale. Magic will never crash, right? Because it's going to be always smooth. So it's sort of a magical trick because the thing will never blow up. So it sounds like, wow, amazing solution, You just do that, and that's it. You're in the big rig. So, but still, I'm not sure you want that, simply because when you do that, you have a lot of side effects. The first one is that you have a lot of parametric conservation, simply because you are starting to introduce some artificial viscosity, which are not properly compensated by the viscous dissipation in the entropy equation, for instance. You have a lot of wrong dissipation range. Obviously, the scales in your spectra is going to be completely artificial and controlled by the beta parameter that you cast in there. You break up all your cascade, and so forth, and so on. So if you want to use it, make sure why you want to use it, during it, and try to run, at least in some parameter range, cases with and without to see how it changes your properties, and possibly try to do some amplitude study. So try to change the prefactor that enters the hyperdiffusion here, divide it successively by 10 and 10 and 10 to see whether you converge or if it's completely garbage what you're doing. So use it with care, and I wouldn't recommend it to use it at all, actually, but yeah, just you can use it for transient, I would say. It's again helping a lot for transient phases. But possibly you're introducing some non-physical effects in there. So because it's just a artificial Laplace thingy coming in. Okay, I think it's time to conclude for me. So this is sort of recipes or takeaway message that I want to list. So the first thing, obviously, is that you identify what you want to do. What is the physical problems you want to address? And the underlying question is, what kind of parameter range do you want to cover in terms of Ekman and Rayleigh number? And the side question is, what is your computational resources? Do you have 10,000 CPU hours? Do you have 1 million CPU hours? Do you have 10 million? And then it will possibly change what you can do, right? The third step is define the appropriate resolution, spatial and temporal resolution you need. As a rule of thumb, I would follow the Ekman 1/3 rule, but be careful so that there are a lot of additional complexities, especially when Reynolds number gets larger and larger, that will break up this rule and make your convergence criteria much stricter than this kind of rule. Well, especially for those of you who might have heard about Ekman boundary layer, most of you already know that, or those of you who knows what an Ekman boundary layer is, know that it follows an Ekman 1/2, which is much steeper than Ekman 1/3. So if you just follow this step here, ultimately you won't have enough point in you to resolve properly your Ekman boundary layer. So maybe an issue here. Okay, the first step is always check, always look at your solution. So look at your local quantities, look at the spectra, and possibly refine your grid. So you finish your run, you seem to be happy with it, but why not be running a little bit longer with a better grid to see if something changes or not? The fifth step is, well, try to be clever. You don't want to waste your time in the transient phases. And there are some, luckily there are some available tricks. So you can use like a slightly under-resolved solution during the transient. You can use symmetries. You can follow a meaningful path in the parameter space. If you have some a priori feeling on how the system should be, it can help. You don't want to over-resolve, and you can use symmetries, I said that. And the last thing is that don't take me too serious here, because it's really a serious deal, this resolution issue problems. It's a very complicated topic, and well, there is no final answer in this talk, I think. So it's sort of a final thing. And there's a sort of little joke here. So what you see here is probably one of the longest ongoing experiment available here. This is the so-called pitch drop experiment, which was initiated by Thomas Panel in University of Queensland in 1927. And at that stage, he found sort of a very special material, which is called pitch. And at that stage, he didn't know if it was a fluid or not at all. So what he did is that, well, he put some of this pitch into this sort of tank, and he just checked whether it could flow or not at all. And after 10 years, what happened actually that it formed a droplet, and this droplet went down. So I said, well, actually it's a fluid, and this experiment, well, it's still running, and it's like 90 years it's running, and it formed 10 droplets during this 90 years. So the conclusion was pitch is 10 to 11 times more viscous than water. Oh, that sounds like something I'm actually doing in my numerical model, right? So just think about like a big rotating planetary core with this diameter, which looks very similar to the Earth's core, with this rotation rate, which looks also very similar to the Earth's core, but now fill it with this pitch. What would be the Ekman number? Well, the Ekman number would be 10 to minus 4. So that's it. I'll leave you draw your own conclusion based on that. Do you have any questions? Yes.
If you make a simulation with magic at the lowest condition, and so on the quarter of the sphere, can you use the Vista file directly in the higher?
Yeah.
Just put it like this.
Yeah. Magic is capable of remapping your data on a different grid. So basically, if you extrapolate, it just sets the new coefficient to 0 by default. So there is no fancy cascade or whatever approximation to fill the missing Gauss coefficient in there.
That depends. I mean, in radius we do that. We do an interpolation.
Yeah, in radius, if you
but not in spherical harmonics. Just the ones remain 0 to start with that were not in the restart file. But then you quickly fill them in.
So what I would recommend if you use like symmetries and remove it is like put some noise again, because otherwise your spectra will start at 0. So if say I have like this run that is finished with a fourfold symmetry, so which means that like there is only 1/4 of the azimuthal or the m's which are there, and all the other m's are set to 0. Now I want to run it full sphere. So as you said, you can just put the restart file and continue and just change blink in the name list. But if you do that, the input energy in the other M is going to be extremely tiny. It's going to be just the machine precision roughly. So if you want to ease it a little bit, you can just put a little bit of noise. So you can put some random noise. It's going to feel a little bit the spherical harmonics with some amplitude, which is going to be tiny, but still there is something, and it's going to speed up a little bit. Cascade build up. But if your system is turbulent, it should be fast. I mean, usually it's really fast to remove this symmetry, at least in convection. I mean, magnetic is always. Any other question? Yes.
So you said we can follow some path in the parameter space.
Yeah.
Is there any way to avoid such effects, like if you have hysteresis or some subcritical stability?
Oh yeah, that's
so
yeah.
You miss something.
Yeah, sure. No, I mean.
But there's no. Is there any way to?
No, I mean, that's a very good point. I mean, if you want to explore this, then you have no choice. You have to pay for it. So you have to start your simulation from 0 and check what's the influence of the initial condition. Okay. I mean, the path I provided is more like a sort of big quotes Earth's way. I mean, if you want to decrease your Ekman number, that's the way to go. But in case, if you want to do some physical parameter analysis at a given Ekman and see whether you have some bistability, some strong field solution or whatever, then you have really to investigate deeply what's the impact of your initial condition, and in that case, it's much better to start from 0 or whatever that you control the field and not restart from another one. But you might not be able simply to do it at low Ekman, right? At low Ekman, it's just impossible because your transient would be too long.
Yeah, so a lot of this we've learned the hard time, right? So we ran simulations for months, and then at the end we had to admit, okay, this was unresolved or something strange happened. something that happened quite frequently in the past was that the time step also was too large, right? So we left it too large, and then actually some strange inertial waves crept in. Remember, inertial waves is something that happens on the rotation time scale. So if your time step is not shorter than the rotation time scale, these waves are not properly resolved. And these are dissipation-less waves, at least in theory, so they're easily to excite. So you have to resolve on these timescales properly to get, to not excite them. And I mean, if you then looked at your solutions, you would see that it looks very strange, nothing like convection. So very large scale, strange runs. And also, if you check the kinetic energy, you have some, not conservation, so suddenly there was a huge peak coming from nowhere. So energy was also not conserved in that case. So we have now additional safety measures in the code, I think. So, but
well, still, I mean, as long as
the code allows to check now for conservation of energy as well.
But still, I mean, that's, well, this you can exclude if you look carefully at your solution. You should be able to exclude it right away. So if you see something, so if you feel that the spatial resolution should be fine, but something weird happened, it might be what Johannes discussed, that the maximum time step is too large, then you have to.
That depends also on Ekman numbers.
Exactly.
So if you have large Ekman numbers, that basically means diffusion is very large. So any strange solution which is not the preferred one, is damped away, maybe, right? But if Ekman number becomes small, you may run into trouble. So all kind of spurious modes may survive simply because viscosity doesn't damp them away. Okay, with that, we can start with a coffee break. And Anke is not here. The next session is again Anke's session. So I think let's take half an hour coffee break.
Voll biologisch. Wenn sich da mal was abschneiden. Aber das ist nicht so beim Garantie. So. Ach, scheiße, jetzt habe ich die Flasche ein bisschen gezogen. Ja. Ist das Montag? Geht das Montag los? 10. Ja, können wir das machen?
Yeah, that's great.
That's 2 hours.
No, for you it will take.
Thank you for your. Yeah. So. Wow. Besides, you're my last year.
What?
You're my last year.
Sir?
Like some compressor.
That is really compressible. You need divergence U equals 0 for spectrum. Else
You need divergence B equals 0 for everything.
divergence U equals 0 to decompose U into yes. That's why. You don't have that.
We can have the compressive spherical symmetrical. Spherical is spherical and spectral. You can.
And then you need to go to vector spherical harmonics.
Yes.
You don't have this simple colloidal duality.
No. I know.
And no one has written something like that.
There is a model. There are things that put the model for vector spherical. By the way, I found a way to do that. Because I actually have to. It was not written explicitly there, and actually I think that the code was right. But I found a workaround.
So you were using colloidal with
Now, even in a linear code, you need I use a workaround.
Oh, it's just y with r plus grad y.
Run.
Plus curl of
One extra brain, which
I'm actually there is.
hat keine History.
So how do you do it?
Wenn man dieses System mal nicht nutzt.
Ja.
I mean, I found it my way, and then I found it was the same thing. I mean, at least that's so how much I'm sure I'm good. So if you have a violin, something scalar field.
sorry.
And you get the answer. But the gradient of P is not. It's, for instance, can be y plus gradient of y plus
Anyway, then you have to try this by next week or something. Or just send me a PDF to print it. Yeah. Are you coming to the dinner?
So what to do is that you use the spherical
Where are you staying? The one without kitchen.
to record. To do, for example, the divergence of this guy or the curl of this guy. You simply
Express the vector. And your for you is close. It's close. Right, so it's all yeah, but okay.
And
Yeah.
this
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 is
guy here. It's
So I will just come to the dinner. I will be there around 7. So where I
You know where the place is?
how you are going with the parcel?
I have no idea.
Yeah, where so it's kind of okay.
so you use this proper electron.
Yeah.
This guy is exactly y plus 1 and y plus 1.
Yes.
And then calculate the guy always with the same scalars. Cool. And then at the end, so you if you want to calculate something very this guy, you make 1, and then at the end you divide by without calling. I just have one comment. Maybe actually much nicer to have this because they want something about checking.
Yeah.
Checking. I mean, at the end, divergence of code are just a checking operation with efficiency instead of doing this, all these machines.
So are you still working on that? Your whole life is
Which I never use, by the way. It's too early. And I tried to get and anyway, how will magic perform the 800 points a time step of 1 second? Simulation for 3 months. How much time will magic need? How much time? That's grid of 800 points. Yeah, I mean, whatever. Pick whatever you want. If this time step is to 2048 more. 1 second. But how many times? It's 10 meters. Yeah, holy cow, 800 good points. Use radius is compass. That's the problem. How much time does magic requires to do this? I want to make
I would give it a try because you have to see, where the communication gets set up.
yes, exactly.
Yeah, so I'll send you the wall time and then we can see how it takes.
But the point, I think the main point is this. Because you don't have to.
No, we can go like
And still, 3 months with, 10 pounds, and I need that because I need it for my spectrum resolution.
Sure, I'll run it on the on that cluster. I'll put scales like so we ran with the field like and scaled up to 4800. That's the maximum we can go in.
I mean, it's so well because it's fully spectral.
It's not fully spectral.
But Shemshem is spectral. It's fully spectral in space.
Yeah, so that's linear terms of conjugation.
Yes, but not so that's
All the way around. Who is famous for implementing the baskets. Yeah, this guy is famous for baskets. And we implemented
that this library is and the wall time reduced by half. Before that, we were using English time rulers. And using this library, this also uses
I mean, if you look at the spherical and transform, the class is very simple. I mean, it's not very simple, it's just. It's a readable amount of time. The machinery where it's parallelized, so I don't know. A lot of auxiliary variables.
Oh, I found like that in portions of matter. Something called a class. It's supposed to do some kind of transform. And then the function A, B, C, D. and then it says work 1, work 2. And then you have A equals B equals going on.
I mean, actually, most of the time, my approach, I think you spend half of the time to go to the spectral one, half the time to the rest. So it's very slow.
So we reducing the wall time transitions.
Yeah. I mean, it's actually very fast in the spectral. It's more than 50. And therefore. Yes, that's the library we're studying. Yeah, that's the library that's also discussed.
Yeah, it does.
Yes, that's actually exactly the library you want to do. I found this library 2 years ago, but I said
yeah, very special.
it's simply that.
So you can try.
It's very crowded, but it's very crowded.
You can try.
But there is also a Python module, so you can directly test it.
Spend a long time. When you do make it shows this fancy stuff in green and shows percentage of compilation. It's really fancy.
Yeah, you may need to get
Also, we spent a long time trying to adapt our shells to all kinds of shells. And I had really hard time adapting to form. And people who use corn should not develop the shell script and to set the correct path to detect the Python modules and set the Python backend.
It is for post-processing.
Not just post-processing, also if you want to test the code, it takes your memory. So we wrote scientists. We wrote a magical shell script command with these 2 lines, you know. So one command goes into another, but you can like 5 minutes to get the compiler that
So what are you going to do essentially?
Everything works out for you collect the results from this, and then run a Python script. It really gave me contours of different I mean, I'm sure I can do the errors first when running the script because I don't run it before.
But it's 2 hours.
Yes, of course. I have to do my favorites. So probably first overall spending fixing errors in Python script.
It's true.
Actually, yeah, that's
What is it?
Half an hour.
So, but it's power.
Yeah. Just search this on Google. We also have proposals.
So why don't you usually look for that?
So if you go to this, you go to yeah, there's no sense. I'm the IT guy. I'm the IT guy. Yes. Yeah.
This must have been broken.
You want to look at my slides?
No, no, it's just very short. So I assume it's going to be right. Yeah. Maybe you can start anyway with visualization of your data.
Yeah, so that's the last part of my last.
So it seems that like the makeup of an Italian body, or like a guy who has some Italian background, and it seems that the Italian, I mean, he's sharing the office with the other guy. It seems that he put some Italian flag on the door.
Did you put the British in this picture?
Maybe not. So it's something that he's having fun. It seems that he's having fun.
It's just complaining about the fucking expensive stuff.
Well, I mean, compared to now,
But then it's fine. Yes. Like this place. Are you having fun with the new Italian film? I'm fine with it.
It's not the same.
Not the same.
Christian life.
Did you got this? No.
I won't go stay there.
September 2016.
My gosh,
When he was around.
then you get the numbers right away, and that's it.
Let me get far. From a question to the next.
You said, I'm sending an application that Thomas Agustin in Paris.
If you want to do some job. If you want to do some microwaves in the score.
Yeah.
What? Microwaves in the core.
Thinking what waves?
Microwaves.
Mac.
Or magneto.
Mac.
So it's energy waves. But special magnetic waves, like also the core is worse than storing cores.
Well, just do a brute force. So we were discussing this, but Universe is going to be more expensive. So we were discussing if you can do this. 10 millions of time steps with 800 green points. How much time is that? How many green points do we need? That's the whole thing. Well, we say he wants to do the fences now, so I don't know how. I mean, 800 in radius and every 100 seems weird.
No, it's not weird if you want to resolve.
No, that's not weird. That's typically what Ash did for this gravity wave. It's paper by Alban and Brown. Yeah, they had really like 2,024 radius and 10 miles equal.
Because you need to resolve the radius.
I have no idea.
Yeah, but that's the number of grid points we need to find.
No, Cheb or Penitent.
I use find if
Then we change that to compile.
yeah, but you need to resolve the wave. But it's not.
But there is no acoustic waves in the
Yes, that's
a side where
I have a spectral code.
And I do this kind of stuff.
But then how does it take one time step which is stuff?
No, so right. So my problem is no. My problem is that
3 years of the time.
for Aliport
3 years.
I use Aliport 3. So with Aliport 3,
Oh yeah.
I do 10 times the percent. And I limited
So one decode.
no.
No, but then I code 3. Come on, it's like how many 3 harmonic you have? Like 3. Yeah, but you have ends as well, I suppose.
Yeah, so it's all
Yeah,
it's
the number of things that happen.
But with
So it's like
5 is 2 to 1. Yeah, because my problem is that I can only parallelize a straight one.
Yeah, because
So far, I cannot parallelize.
so I'm radius.
I can parallelize it.
Oh shit.
Yes, I actually want to change that.
But you can parallelize it as well, I suppose.
Yes, parallelizing.
But then code 3.
No, it's.
That's like,
I mean, each core must have the same. So each core is the first.
Okay, to balance that. But if you have M equals 2, two sections. One is M equals 0. One and 2.
Exactly. Yeah. So my computational cost score is like most.
Das sieht schön aus. Wenn ich dann vorher der CMB ausgesucht jetzt für dann baut er automatisch, muss ich dann noch.
I mean, it's fully implicit.
Yeah.
Also das wäre schon. Aber du hast halt wenig Kontrolle.
Yeah, exactly.
I mean, it's explicit.
Yeah.
So,
So,
du kannst ja das
I mean,
nicht lösen.
yeah,
Und unten rein. Und dann deswegen die Randbedingungen, dann kannst du einfach die Personsspeicherung lösen. Das heißt, in der Animation ist dann schlussendlich nur der konvektierende Teil drin. Wenn ihr so zum Beispiel Nachdruckcase macht, einen großen Dornrelais da unten drauf. Also der ist super angebracht. Der ist super angebracht. Aber da ist auch der Diffusiv. Die kannst du auch ausrechnen, wenn du halt die Welle zwar super einstellst, aber kein Problem. Dann kriegst du halt ein diffusives Profil und dann siehst du halt,
why should I use it?
und dann
No, what he wants to ask is why do you have that requirement to the boundary?
irgendwo hast du den tollen das definiert dann immer.
So, but in my case, I need that.
but it means the velocity is doing something.
Aber das kannst du nicht
The radial.
So,
Stopping, right?
So
You have some boundaries. You want
Das war der Time Step, das ist ein Verhältnis von Soundspeed, von dem was unten rein
yeah. Well, anyway, it's downstream in our model. The reality.
Das macht man dann so und dann hat man es und
aber das ist
arbeitet dann und
this grid with the grid kind of that essentially what was the whole time?
Good. Was was the
1,100. No, and it was with the correlation, so we can bring that down to 2.5 seconds.
And how many secrets? Fängt wir an.
About 1,500.
Legst du die 90 Flips unten ins Tor, der obere rechts zu, und dann nimmst du die. You basically 1 month to see every month, 2 months to see
Real time stuff.
Real time stuff, yeah. I just because every day.
But if I restrict to equals 3.
Yeah, if you restrict to equals 3 should be.
I don't know. Never tried. I think the code will not be efficient.
Yeah, it's supposed to be efficient.
PI transport.
Ja, also was wir machen.
I mean, it will be like.
Ich gehe jetzt raus für die
But already ansonsten die Boundary Layers, die irgendwo
das ist eine einfache tatsächliche das ist ein Radius und nimmt an als das ist aber das ist meine Ordnung, alles was da raus an und das ist halt der
But I mean, the polarization and radiation should do the whole thing.
Yeah. I mean,
Order of the domain.
I can get
kein Problem.
I can hear you.
100 if they keep points.
With 1.4.
And then I need to communicate from there.
Yeah.
Okay, I have to spend time.
The so-called kids time.
What the hell is amazing?
Wow. That's cool.
Well, at least it's saturated. I guess.
It's still bad water, so don't complain. Actually, that's funny because the initial energy was correct or close to the final. And it went up, it came down. So you found a strong field Dormy solution, maybe? Very strong field and went down. Too bad. You're back to my
It's change of around. Yeah, but till here it was. No, wait. You started from here, right? Or do you have all the runs in the same directory? Do you have all the runs in the same directory?
I started from the research file.
That's weird. So the transient went out, and then it can run.
That can happen.
Plus kinetic, yes. Yeah.
So.
Okay.
It shows what you see plugs into the system. So
Yes.
So this can change over time.
No, it's fixed temperature. Fixed temperature.
So you can go in both ways.
Fixed temperature difference.
In the bottom one.
Yes. So the bottom is cheapest because here the top is cheap.
But it's fixed. Yeah, so what is that? Do I switch to multiple case? This is PM4. I have PM4, which is very.
Yes, it is on the borderline. This is the mechanical.
But it's just a dipole.
No, it's so the red is colored. Yeah, the red is toroidal, blue is colored.
but it's not one of the parts entirely.
And the dash also that.
Yeah, so it could be first it still tries to establish dipole, but then it fails, and then it goes down.
But multiple doesn't necessarily mean low energy.
Not necessarily, but right in the transition.
Well, you can look at the divergence. So if you do magic TSR, so that's CMB.
So,
step one.
sometimes you have just weird concept. Maybe you should be able to see, but that shows it's still back there, right? So it's back
At CMB, yes.
but in the theory, something changes. So definitely, we go from the simple solution to some for 15 or X. Spectral.
Do you have it? First, let's try just do an LS star spec star. But during the benchmark. Yeah, you need to copy and paste.
Just click this mouse.
Let me see the copy and paste.
Yeah. So, Alex, we have stack.
Oh, because I guess. Yeah. So if you do a tail of this, tail of normal. Okay, it's run. So I guess it just runs up time.
So one, because you get the output of the spectrum again.
No, you get it at regular intervals.
So we have, 79,000 and we wanted 5 spectrum and 1,000.
That's nothing way different, so nice. That's weird. What, did you use the same way? 33. Oh yeah, it does. If you go to the top, if you can do a fuser, if you still running. You can if you run technique for 1 time, then you.
So what step? What scheme do you have?
It's your code. So but the sound of 0.6.
Yeah. So I have the spectrum that takes in the region.
So you take half of present, half of past.
Both my rounds are 27.
And then you go to the pictures.
So something like that. Otherwise,
Yeah, sure. Did you export this?
Check.
And also anything you write outside, I mean, it's not perfect.
So let's check whether the others have
Yeah, just because they can see you what's done. No, it's not that.
start again? I mean,
Yes.
You still want to talk to spherical
Probably. I remember.
Could I see first show again?
Oh, yeah.
There's somebody wants to speak. Okay, last session for today. I start with telling you where we have the dinner. Can you see the map or less? So Google Maps. In the moment, we are at the North Campus, which is here, and then the city center is right here. So, well, I guess most of you know this by now. So you follow this road, and then down here, and then you come to the pedestrian zone, which is here. And right in the center of this, it says Gänsewiesel. This is actually where the old marketplace is. And at this old marketplace is a famous, he's famous in Göttingen, a little statue, which is called the Gänsewiesel, and it's on top of a fountain. So this is, so you come from here, if we go down the main road towards the city center, the big road, right? 27. You arrive here, and then the pedestrian zone starts, and you keep on walking straight. And at some point, you are here at the old marketplace, and that's where it says Gänsewiesel. And well, maybe I can switch now to satellite. That's fast enough. So this is the marketplace, the old marketplace. This is the old Rathaus, Göttingen Rathaus, and in front of that there is this fountain, and on top of the fountain is the Gänsewiesel, which is this little figure here, and it has a big tradition in Germany, but we can talk about it when we're there. But so we can meet in front of the Gänsewiesel at, you know, a little bit before 7 or something. We're supposed to start at 7, so right at the marketplace, can't miss it. And if you want to go to the restaurant directly, it's here. It's called Kreuzgang. There's one report, so it may not be very good, so don't read it. So you know, and it's not so easy to see because there is just this entrance. You see this entrance there, and then you have to go down into the cellar. So the actual restaurant is in the cellar. Okay, but we can meet at the Gänsewiesel, and everybody, I think, just follows. But you can also ask them. So a little bit before at this nice little statue. Okay, your turn.
All right, welcome everyone to the last hands-on session for today. So in the morning, you let the code run with different parameters, and hopefully you are done by now. You're not?
So we specified to run 5.5 hours. They are over now, so code should all be finished. Whether they gave some useful results, we don't know. That's something we have to check.
If you set top on your machines, does it just show magic?
No, it's finished.
Okay, fine. Okay.
I was.
All right. So now we'll get time average parameters out of these runs. So like yesterday, if you do, if you say
first people can look into the log file and find out how long it actually ran. Do you want to do that? Okay.
Yeah.
Just edit the log file. Yeah, maybe that's a good idea.
So if you look into your log files, at the end it should tell you how long it ran, and if it crashed in between. So if it says it successfully ran, then it ran successfully, of course. And if it ran successfully, now you can proceed to the Python stuff.
So let's first ask what people see.
Regular end of program.
That sounds good. So
that sounds good.
How many time steps did you actually integrate for?
114.000.
114,000.
527.
And you? So how many time steps did you? So who has the most number of time steps? Who's the winner? Anke was planning for 400,000 time steps in this time. Does anybody have 400,000 time steps in 5.5 hours? So how much do you have, Julian? 100,000. Anybody more than 100,600? 200,000? Exactly 200,000? Martin is the winner. So, well, I have only 74,000, so I did something terribly wrong, obviously. 121? 121? yeah, we were both running on the same machine, so something with this machine probably was not. So in theory, of course, if you have the machine for yourself or the node for yourself, it should always give you the same number. But there may be other processes running on the machine, or there may be conflicts between the processes running on the machine. And I think that must have happened here, because Ankit tested it, and he was able to run the 400,000 time steps in 5.5 hours. But he was alone on the machine, nobody else doing anything. And obviously that helped him a lot.
Very optimistic.
Very optimistic. So I think what happened is there may have been communication issues. So with 4 runs running on one node, I think the communication issues popped in, and that probably slowed it down. So now the question is whether the shorter runs are still useful. So the question is whether we have equilibrated. So we always have the transient at first. So if you,
So something like that.
so maybe you can look at the magnetic energy first. Everybody can try to do that.
Can you show the
commands again?
Yeah. Yeah. Yes, but just the first part.
Just the first part, and then you can. Also er nimmt halt die 400.000.
So if you import everything from Magic and look at the magnetic energy, it should have a transient and then it should have saturated at some point. And the place where it saturates, you select. Yeah, not as flat as this one. There will be tiny wiggles, but where you feel it has more or less saturated, you select your starting point of average, which is the T start here.
Aber Markus, was ich dann mache, ist, du kannst einfach. Kannst du das und vielleicht auch ein Spektrum. Bisher war ein Aber es gibt eben auch andere Möglichkeiten, die auch zu steuern. Also zum Beispiel die richtigen Stats, das 10.000 oder alle 10.000 Zeitschritten. Du kannst auch DT haben, das Graph sagen. Kannst du dann an den Zeitabschnitten schreiben. Also wir hatten jetzt zum Beispiel ungefähr, ich weiß nicht wie lange du, bei mir ist es ungefähr 9 Zeiteinheiten oder 8 Zeiteinheiten gelaufen. Das ist jetzt aber die Diskurs. Vielleicht zum Beispiel DT 1 angewendet ist. So, ich mache das jetzt auch noch mal.
Also, wenn du sonst nicht meine
Ja. Okay, nochmal.
Also so scheint das auch als ein
Ja.
von
Weil là, il y a quand même.
So, so you may not be perfectly happy with your runs for the reason that, well, the runs were shorter than anticipated, and therefore you may not have a G file, so a graphics output file, and you may not have a spectrum file. Because they were supposed to be only produced after some time steps. And if your runs were too short, you won't have that. So what we typically do if these are missing, you still have the restart file. So you can use the restart file for a new run. So start exactly where you ended, and then you just have to run for a few time steps to make the code basically calculate all the output, so 2, 3, 4. I just tried it with 1, it doesn't work, but with 4, for example, it worked. And this is basically finished like that. So you create a new name list by copying the old name list, basically, everything the same, except you change the restart file, using the restart file that you produced from the run you started this morning. And then don't forget to change the tag that you don't overwrite the first run. I mean, it wouldn't do it, but give that an additional, well, a little bit different name. I call it, for example, just and added a B to the end or something like that. So that you have a second run then using the restart file from the first one. And this should then produce G files and also spectra. And these we may want to visualize.
Genau, genau. Und ja, ich habe immer eine Idee, aber wie das überschreiben. Und dann man aus 6 auf nur 4 oder 5 Stück. Aber da hätte er uns ja auch alles.
Wir können ja nochmal den anderen
Ich hatte auch mal den
wahrscheinlich, weil das so angezeigt war, man
I don't know what kind of build. Maybe it's not. The Marcus is doing it's nice.
G files, graphic output files, and spectral files now.
Well, there are just two.
Okay, and we have nice solutions. Do you have decision and solutions are equilibrated? When you look at the magnetic energies, so something that existingly seem to remain the same. Some of them should have time-dependent solutions. Maybe not. Yeah. We had a big one. Yeah, nevertheless, no. Okay, but
Yeah, okay.
it really doesn't matter. So, yeah,
I don't mean the
but easy. We have to look at the spectrum. And we'll see. So, okay, I think you can.
But I mean, like there are several groups which
Also,
because some started from the wrong solution, some have changed PRs.
Okay, es geht nur, wenn man es
Well, we can try. Get started.
Yeah, so should we start?
So the zero coverage.
The average field that you have to put a dish down on there's a factor zero.
So even I have.
Maybe 7.
Yeah, what do you think?
Maybe if you go to bug skills.
That is, I mean, still. Those stuff, but nevertheless, I think it's try. So. So should we first try to find out how many people have a useful solution?
Well, I can what you call a useful solution.
Yes. Yeah, but also just like we ran on the same machine, so there are maybe because we did fire at the same time.
Ja gut, aber ist ja anders benannt. Genau, so benannt die wieder beide sind von den anderen. Erstmal die Tür. Bei der einen. Wir können jetzt nochmal.
So then it's just random. Saying anything about the very good like now.
Okay. Ja, die könnte man jetzt mal ausprobieren. Da muss man aber nach vorne was machen, indem man das letzte Feld, glaube ich, genau. Genau, das, also das mal die Vertical.
So there is this
Ich habe dann gleich Ideen im Quartier. Bei dem hier, ich habe keine Ahnung, welchen Vertical der da hier. Also für die Parallose. Ja, das stimmt. Ich frage mich aber nur gerade, wo man sagen kann, welcher der. Also nicht aktuell, sondern auch mal nochmal irgendwo sagen kann, ich interessiere den ersten oder den zweiten oder den dritten. Machen aber nicht jetzt einfach.
Ja, was siehst du da? Was siehst du
so additional voice.
dass der Mittelwert durch die Kurve ist. Das hier ist
So that means this additional but depending on the medium here for some reason m equals 2 was something which was close from us.
Es läuft. Was läuft?
Ja. But these two are a bit stronger than these, right?
Ja, da kann man dann mal kann man
Oh, das ist genre. J'ai jamais pensé.
Ah ja, schon bei Statistiken kommt auch immer noch auf, wenn man sich schon eingefügt hat. Aber ich meine, was soll das? Das ist ja auch kleiner, was ist das da?
Greater than 2 is random.
So we have several problems. It's good that you're still trying and you make the best out of it. So I guess all of you have some solution. You can visualize them. They're not necessarily the solution we wanted to have. So one issue is that obviously we underestimated the runtime that you would need. So nobody got the 400,000 timestamps, right? Did that? That means some of the results you have are not equilibrated enough. Some are, others are not. Second, and the reason, as I said, is because I could try this alone on one node and nothing was happening, so he got all the runtime on one node and I could share it. And that seems to be an issue, probably communication issue. People run with the node and they have to share the memory bandwidth, and that he didn't calculate correctly. So the second issue is that if you look at a lot of solutions that you have, and you look at the spectrum, I don't know whether you did that, you see basically so that not all the wave numbers are excited. So if you all look at the spectral files, probably not. So you should have the keen underscore spec something file. So check whether you have that. So does somebody has no keen spec file? So if your run was too short, I mean, we basically told the code how many restart files we want, or after how many times that we want the first one, right? By basically telling the code how many spectrum files we wanted, for example, right? But if the run was too short, he never may have reached that point. I mean, that's something that actually is worse in the new version than in the old version, because in the old version, it was made sure that if you have specified any, if you want a restart file, there is one written at the end, no matter what, right? So maybe we should change the spec. But so if you don't, does anybody have no keen underscore spec file? Everybody has one, so that's great. Now you can either edit this. So if you just edit it, just put it on the screen, you will find several columns. Obviously, there's also a tool to visualize it, but I don't know that. So that's just magic spectrum. It's just magic spectrum Python. But if you look at the
capital M, capital S, magic spectrum.
So you can either look at it by just editing it, then you will find several columns. The first column is just the degree or order. The third column is degree and order. The second column is the energy in the specific mode versus degree. And that should be basically filled, except degree 0. There's nothing. Because there is no solution with L equals 0. And not part of the solution space. The second column, or the third column I should say, is now the spectrum versus spherical harmonic order. So the wave number. And in the benchmark, we would just have wave number 0 to the x-axis part, or basically just wave number 4. Because 4 columns, and we might have higher harmonic 8 columns. And some of us have now a wave number 2 solution. So you see energy in the x-symmetric part, and if you have visualized the spectrum, the spectrum peak is the x-symmetric. And then you have more energy and equals to wave number 2, 4, and 6. That means not all wave numbers are exact. You still have all of them. You should have basically no symmetry according to our computation. So the problem is that you started with something which has a symmetry in it, and ultimately, if you run your code long enough, all the other modes may be excited as well, but this may take a long time because you just excite them with basically numerical noise. Unless you wait, your regular number is very large. Some of you have not a very large number. So what you can do is you can add noise right from the beginning.
And if I want to
you can add noise to your run.
The data, the raw data is now.
And I suggest what we do is that we rerun these cases, but now basically the same run, adding noise as well.
Okay.
Right?
And we try continuing it
Yeah.
actually from this, and it takes like maybe 4,000 times that.
Then you have other wave numbers.
Rebuild
Yeah.
at the same amplitude as the rest. So it's really correct.
So you suggest we just take what we have
Oh yeah, sure.
and then
Add
just
some noise.
add noise to that. Okay, so what you do is you create a new name list based on the old name list. Some of you have done this already to get a key file or a spectral file. So just create another one using the restart file from the run you started this morning.
Oh, yeah.
And then, drop the info. And then Ankit will tell you now what you have to add to get some noise into the velocity field. So you have to add init v1 equals 3. And this number just tells you the noise spectrum. So, and then amp v1 equals a small number, so it should be noise, so it should be 10 to the minus 2 or something. Doesn't really matter too much. So that means you start with noise of the amplitude 10 to the minus 2 at degree and order 1. And then the 3 in the init v1 means that your degree spectrum is decaying like power 3. Right, so that the high degrees, they're not excited usually, so you don't need edge cross noise in that. So that defines a noise spectrum that you add to your restart file. And then in addition, you just run it shorter. So so we change that to 5,000 steps. Well, 5,000, is that okay? What do you think? 5,000? N times steps.
Fine, well,
Yeah, let's try it with that.
I mean, you can even go 10,000.
Yes, okay. If you just have everybody starts just one run, that may work. And then you need to change the tag so that you don't overwrite old results. Actually, you cannot. So if you don't specify a new tag, your run will stop and tell you. And it cannot overwrite old files.
So, are we supposed to add some noise for the annual fee?
No, it's enough to do it for one. Then transfer it to the other.
Do it again anyway, because we didn't have to done.
But I think you have this your solution is more or less able to support symmetries. Means that only the spectral harmonic order 4 was excited. Because you started with a solution that had a 4-4 symmetry. The symmetries were not excited at all. So they initialized with 0 and they remained at 0. So if you add this random noise now, they will.
Lass uns mal wieder nur eine.
Very fast.
Wieder nur 8%.
Da wollte ich noch mal was feststellen.
Then the other one.
It's just like 5.
Yeah, it was 5.4 from the morning.
The initially set up morning was benchmark.
Yeah.
And that's just the most
Your other ones are not even initialized.
Okay. The other one here doesn't have.
Which, yeah, that's so that's the one that you can check the resolution.
Yeah. So now we should start it again because random noise. Gut. Wieder Infrequenz?
Ja, ich glaube das.
Nee, ich habe keine Infrequenz.
Ja. Ja, und damals